My name is Pavel. I work at Align Technology. And today we'll discuss constructors and destructors, but not in the sense that they are meant to establish invariants when you construct an object, and when you destruct an object, you want to check that invariants are preserved. And in today's talk, we will discuss more like tricks and pitfalls and nitpicks of how you can code constructors and destructors. So I hope everyone got here who wanted to get here. So let's start. We'll discuss today the famous or infamous rule of 0, rule of 3, rule of 5, and can we break them and when can we break them? Next, we'll discuss copying and moving and equivalency, what equivalency means, or rather, what effects does it have? Constructor overloading and its pitfalls, explicit constructors, constexpr constructors and destructors, and regarding destructors, we'll discuss that they are noexcept by default since C++, whatever, 17, let's say. I don't remember exactly when they started to be noexcept by default. Next, destructors should be virtual for polymorphic types, and we'll conclude with a bit of glimpse into C++20 with constrained destructors. So before we begin, please head over to the link that you see on the slide. And I started the live session there. And I will ask you questions and expect you to answer them for fun. You don't have to if you don't want to, but I encourage you to try to answer them. So for people watching the recording at home, we'll have a dedicated quiz that repeats all the questions, so you can answer them with the talk, with the recording at home when you watch it. And we don't have answers so far. Oh, I didn't. Sorry. I didn't start to receive answers. So now you can vote. So the first question is, let's try it. The first question is, what's your level in C++? We have one Andrei Alexandrescu, very glad to see him or to know that he is present, and the rest you can see here. So let's continue our presentation. I will allow to answer the next question, so we don't spend time on waiting for answers, and let's continue. So the first one is the rule of 0, special functions. And it states that if you don't need to declare or define any special functions like constructor, destructor, or copy or move operations, don't do that. So in this case, we have a struct with 2 fields, and we can do all the operations like construct by default, copy construct, and move. And so let's look at Hort-Hinon's table that is very handy for our purpose. And here we see the 3 easy cases, and the rest of them are hard. The rule of 0 is the first row where we define nothing. no special functions, and everything is defaulted by the compiler. In our case, the compiler will generate all the necessary functions, all the necessary special functions for us, and so we can construct, copy, and move objects. This works even if the fields are private. So in this case, we have two private fields, and we have a setter and function print that basically prints the fields. And to demonstrate it, we can write a program like this. And when we set values and then copy, we can see that when we call printed outputs the values that we set, and when we move from that object, we can see that the string was moved out, and what we end up with an empty string, and an int was just copied. But please don't use moved from objects. This is just for demonstration purposes. So next is the rule of 3 special functions. So let's consult Howard-Hinon's table once again, and we see that if we define destructor or one of the copy operations, the other ones are defaulted. And this is kind of scary because the chances are that if you define one of them to manage resources manually, you want to define all of them. So you don't have leaks and you manage properly resources in all of that, on all of those operations. And when you define one of them, all of the move operations are not declared. This is what we want, actually. But the scary part is the copy operations. So, for example, we can write this type copyable. We have default constructor for our convenience to be able to construct an object by default. And we have some kind of resource. And if we define in these 3 special functions manual handling of that resource, we most probably need to define how to handle this resource in all other operations. For example, if we handle it manually in copy constructor, for example, where we clone, then probably we need to add code to free the resource in destructor, and again, add code to assignment operator to properly handle copying operation. So having that, we can do all of these things. We can construct by default, we can copy, and we can copy assign. And when we ask to move an object, the copy constructor is called. So instead of ask to move, we get copy. This is what we want. So the next one is the rule of 5 special functions. Here, it's kind of the same level of scary when we defined only 3 operations, destructor and copy operations. But nevertheless, if you want to make a type copyable and movable, probably you want to define all of the 5 operations, destructor, copy, and move operations, for basically the same reasons. So for the rule of 5, we have core guideline that says that if you define one or delete one of the operations, you want to define or delete or default all of them. So this is basically the basic implementation of copy movable and the type that can be copied and moved. And here are the 5 special functions. that is destruction, copy operations, and move operations. So having that type defined, copyable, movable, we can default construct, we can copy assign, and we can also do move operations with move constructor and move assignment. That's again what we want, what we would want it to do. So the rules are there, but we frequently want to break them and see what happens. So let's break them and see what happens here. So what if we want to make a type movable but non-copyable? So for this purpose, we define move operations, which are noexcept, by the way. So some other operations can guarantee a stronger exception guarantee, can provide a strong exception guarantee. And we delete copy operations. So having this type, we can default construct, we cannot copy assign, but we can move and we can move assign. So now is the question, having that movable, non-copyable type and an object of that type, we want to add that item or some like other object of that type to a collection, in this case, vector. And the question is, which of these push operations will work? Please head over to the quiz site and let's see what we have now, what answers do we have now. And we have a strong preference for one of them. And I will reveal the answer now. And the right answer is B or C. This was kind of a trick question. I'm sorry for that. You had multiple choice, and but yeah, B is correct. The majority answered correctly, but C is also correct because a temporary value can be moved contrast with an object item that we allocated on the stack. So the correct answers in this case are B and C, where we explicitly apply std move to the item, and then we move basically a temporary object. So let's move on. I will allow to answer the next question. And the next kind of experiment is, I should say that looking at the whole adherent table, we can see that if we define only destructor and move operations, we have copy operations deleted by default. So the compiler deletes these operations for you. So actually, when we want to have movable but non-copyable type, we can just omit copy operations, and the compiler will delete them for us. And this, if you squint, really looks like the rule of three. So we have destructor and move constructor and move assignment. And you can find it in the standard library, for example. Unique pointer has move constructor, move assignment, and destructor, and has no defined copy operations. So probably, strictly speaking, at least you don't have to define copy operations when you define move operations, and you don't want to for your type to be copyable. So the next experiment is, let's make the type copyable but non-movable. This is kind of strange, but whatever, let's try it. So here we have default constructor, destructor, move, copy operations, and we delete move operations. So we can construct by default, we can copy, but we cannot move. Movement is prohibited. So the question is, having that type, copyable but non-movable, we want to again add it to a collection vector again in this case. And when we try to move it inside the vector, this doesn't work because we forbade movement. But it seems like we can copy the item into the collection. And so when we try it, we have MSVC standard library to break, to not compile it, to refuse it. And so does libc++ library. It doesn't work with that. But it does work with std libc++, which is GCC default standard library. And the question is, who is right? Let's head over to questions. And we have a strong preference for one variant. Either it is right or it is not right. So let's see the answer. And yes, I'm sorry, this was also a trick question. The majority is incorrect and only one person was right. So let's see how this happens. Why is this happening? So the pushback operation, at least one that is meant to copy an item into the collection, states the requirement that the type has to be copy insertable. So let's see what copy insertable means. And it means that a type is copy insertable if it is also a move insertable, if it satisfies the requirements of move insertable. So in our case, we have deleted the move operations, and movement is explicitly prohibited. So our type does not satisfy the move insertable requirements. So the MSVC and the libc++ standard libraries are right, and GCC's default libstdc++ library is wrong. That's a bug, and somebody should fix it. So let me allow to receive answers for the next questions, and let's move on. So we tried to break the rules, and we see that when we had to move, when we wanted to have movable, non-copyable, we didn't have to define, or rather delete copy operations. And in this case, we tried to break the rule, and it kind of didn't work because we have different requirements that should make the usage of the type reasonable. And in fact, we don't want to break this rule, this concrete rule. So when you want to make your type movable and copyable and movable, rather, you want to define all the 5 special functions. That is destructor, copy operations, and move operations. You can probably to default the copy operations if this is fits your needs. You don't need to explicitly define move operations, but otherwise, or define these move operations or omit them altogether. And then we return to the rule of 3 special functions, and we have only destructor and copy operations. So let's move on. The next topic is copying and moving and equivalency and what it means. And the question to the audience is that we have this gadget type that has default constructor, destructor, and copy constructor. And we have these two programs. And the question is, what will these programs print to the console? Let's head over to the answers side, or question side rather. And we have one answer so far. Don't be shy. I'm not grading you. This is just for your fun. You don't have to do it if you don't want to, but still, I thought that it would be fun. Okay, I will stop receiving answers, and we have two answers, and the majority of people are right that the programs will output at least constructor and destructor, but there is one more correct. There is one more item that is correct. That is in the second program. In the first, okay, let's start with the first program. In the first program, the compiler has to elide the copy operation, but in the second program, the compiler is allowed to elide the copy operation. So both constructor destructor or the sequence of constructor copy destructor destructors are correct. It is defined by the compiler, by the complete compiler. So the standard says that the copy operation can be elided even if the copy or move operation has side effects. And the compiler treats these objects, these virtual objects, like identical or equivalent objects. And basically, it treats them as two ways to refer to the same object. So the takeaway from this is you don't want to have side effects in constructors and move operations that you have to rely on. So because they can be elided, and you will lose that effect, and it will probably break your program. Okay, next topic is, let me allow to answer the next questions. The next topic is constructor overloading. And here you can see two like very similar by semantics constructions. In the first one, the copy constructor is private declared. And in the second one, it is deleted. And we can use that to try to make a copy, but it will not work because, for example, MSIC says that it cannot access private member, or you are attempting to refer to a deleted function, or Clang will say that you are calling private constructor or a deleted constructor. So basically, these two constructions are semantically identical. They forbid to call copy constructor. Why this happens? During copy construction to be overload resolution happens, and for each of these definitions, we have an overload set for fidget, for construction. And both of these declarations go into the overload set. And when the overload happens, it tries to find the best match, and it happens to be the copy construction. In both cases, it is unavailable. So let's see what effects can it have. Here we have a type with three constructors, one default constructor and two constructors, receiving some parameters, and all of them call init function which is private here, and all of them initialize the coolness field, the coolness member. And actually, we don't like it because we have repetition and we would like to get rid of that repetition. But anyway, we have a code in lower right corner that we wrote and it works. And so now, yes, I forgot that I highlighted it. So we have these calls to init repetitive, and we have initialization of the member coolness. So we decided to refactor it and delegate the construction to the private constructor, which receives a coolness parameter that we calculate differently in our other two constructors. And we got rid of the repetition and everything seems well. And the question here is, what will happen to the already existing code? Will it work? Will it continue to work? Let's reveal the answers. Oh, perfect. Oh, no. We had a tie, but at the last moment, one person hopped in. And now we have somewhat tie. One of the answers is correct. One of the items obviously is correct, and one of them is not. So here, let's go back to the slides. So here, because all of these constructors go into the overload set, during the construction, overload resolution happens. And the best match for this construction is the private constructor that receives an int. And the old code that worked before will break. And to fix it, we'll have to go to every place where we provided an integer value to the constructor and change it to double value. And this is not the best outcome that we wanted. So kind of refactoring. And let me allow the answers to flow for the next question. So this also affects inherited constructors. When you inherit a type and inherit constructors, everything goes to the overload set. And in these cases, again, the best match would be the private fidget constructor that receives an int, and both of these both of these cases will not work, even though the gizmo constructor explicitly provides a construction from double. So there is, I think, many ways to fix it, and one of the easiest ways to fix this is to define a type private to the outer type, the initial type, and to use it to pass the value in the private constructor. So in this case, we have very little code to add, but it solves all our problems with the overload resolution because the private constructor doesn't basically participate in the construction outside of this class, of this type. And so even in the case of inherited constructors, this does work. And yeah, let's recap a little bit. So delete unwanted functions or overloads of your overload set. So for non-copyable, for example, it is sufficient to just delete copy operations and have default constructor defined because we want to conveniently inherit from it and we want to be able to construct it by default. The next one is when you overload, keep in mind that private constructors and private functions, for that matter, participate in overload resolution. They go into the overload set, and this can lead to unexpected results. You don't want to surprise your user, so pay attention to that, please. And the last one is kind of controversial because people disagree on this, but I think that you have to pay extra attention and be very cautious when you receive initializer list in your constructors. So like in this infamous example with vector, where you get different results by replacing parentheses with braces. And I would advise to not use initializer list at all, at least in your constructors. So let's move on. The next topic is explicit. Constructors should be explicit by default. And here we get back to our fidgets type, where we now make the constructor that receive parameters explicit. Because when you have, for example, a function fiddle with that receives a fidget, it doesn't make sense to fiddle with 42, at least in my opinion. I hope you agree. But it does make sense to fiddle with fidget that is constructed from some parameter. So please make all your constructors that receive parameters explicit. And even since C++ 98, you could make a constructor that receives multiple parameters explicit. But I wonder, what will we need it for? So let's do something else. Let's refactor some more. Here we have a hypothetical toy example with a function that sets up your order to trade stocks. And it receives the name of the stock. It receives price of the stock to buy, sum that you want to spend buying stocks, price of the stock to sell, and the number of stocks you want to sell. But for the compiler, it looks like this. Compiler has no understanding whatsoever of the parameters. And let's look at an example. In this case, we want to trade the stocks of the sandwich with a pretty big pickle in it corporation. And when you encounter this in the code, you see like this. And most probably you it is hard for you to understand what which parameter means what. So let's refactor it. Let's group the parameters for buying and for selling, and replace the raw parameters with our new types for groups. And it seems that all I need to do now is to add braces. And I think I did a good job refactoring this, and everything is fine now. And the question to the audience, is this actually good? What will happen to me for this change? And we have a tie. Excellent. So let's get back to our slides and discuss what happened. And what happened was that I maybe accidentally swapped the selling parameters with buying parameters. So initially, the order was buying price, money to spend, selling price, and number of stocks to spend. And when I started using the new API, I didn't change the order of the parameters, and now I sell cheap and buy expensive. This is a disaster. So yeah, refactoring. Enter strong types. What we wanted to do is to add an explicit constructor that receives multiple parameters, in this case, price to buy and sum to spend. And for selling parameters, we want to do the same. We want an explicit constructor that receives price to sell and number of stocks. And so if we try to do the same as we did before, it will not work because the constructors are explicit and they will not allow you to construct objects without specifying the type. If we provide the parameters in the wrong order, it will not work, obviously. And only when we guess correctly the order of the parameters, and it will work. And in this case, we'll see that which are buy parameters and which are selling parameters. So I think this is much better than we had before. Much less opportunity to screw up. So it can be made a little bit better with the user-defined literals. In this case, we can specify which one is the amount of money for price or for sum that we want to spend. But we have no time for this, unfortunately. We can come back to that later if we had time in the end. I refer you to this excellent talk by Matt. He discusses, among other things, strong types and in a bit more details that I can allow myself in this talk. And also he discusses some other things that make coding your code more correct. So less opportunity to make mistake. So let's move on. The next thing is constexpr, constructors and destructors. And here we have an aggregate type, a struct that has two members, two fields. And this is a literal type because it's an aggregate and it contains literal types. And we can use it to have constexpr constants like you see here. In C++20, we can use const-init specifier to ensure that it is a compile time constant, not initialized in runtime. So it is allowed to have literal types if we define our constructors constexpr. In this case, we have all the constructors constexpr, and we have trivial destructor, and this makes also this type a literal type. And since this is a literal type, we can do all the same things. We can construct an instance of that type in compile time, a constant in the compile time. So now we can have constexpr destructor, and it doesn't have to be a trivial destructor. And in C++20, if the type has constexpr destructor and constexpr constructors, it also is a literal type. And we can do all the same things, namely to define constants in compile time. So the question is to the audience, if we have a constexpr constructor that has this code that throws exception if the speed is less than 0, what will happen when we try to compile and build and run this program? Let's see the answers. I will reveal the answers. And on average, on the third answered correctly. And let's get back to the slides and see what happens. And yeah, oops. In fact, when sorry, I lost my thought. So when a constructor, when a compiler in a constexpr expression that is evaluated, that is tried to be evaluated in compile time, encounters a throw statement, it causes a compilation error. So in this case, if the fidget constant is evaluated at, in compile time, this will cause a compilation error with the compiler stating something like, in this, during evaluation of this const expression, throw was called, this is forbidden. And this is a good thing because we can validate our parameters, for example, in compile time, rather than in runtime. So what else is there? We can have this naive string implementation, which in Destructor frees the allocated memory, and in the copy constructor from a string from constchar star constructs allocates memory and copies the contents to the allocated memory and stores it. And if we make, surprisingly, both of them constexpr, it will work in some cases. For example, if we have a constexpr function and we use an object of our type string in that function, when the execution leaves the scope, it will call a destructor of the string object. And the rule is that if the allocated memory and deallocated memory match, so the allocated memory has matched the allocation, it is allowed to be done in constexpr functions. So having that, we can now write something like this. We initialize constexpr constant with the result of the call to the process function. And in C++20, this works. So let's see which types are literal types in C++20 also. So basic string and vector become literal types in C++20. Array, we had array already a literal type. We have views, basic string were literal type, and span that we'll have in C++ that we have in C++20 is also a literal type. And all other containers and the adapters like deck, list, borrowed list, sets maps, unordered sets maps, and adapters like queue, priority queue, and stack are not literal types. So in C++20, in constexpr functions, you can now use strings and vectors. This is, I think, useful because you can write one algorithm and use it possibly in both runtime and compile time. Unfortunately, we can't do this. We can't have constexpr constants and in functions or otherwise in global namespace. Because for these instances, we have allocation, but we do not have matched deallocation. And thus this is prohibited by the standard and by the language. The next topic is destructors are noexcept by default. So here we have a type bar, which has default constructor and destructor, and we can use it like this. in the full function. And when an exception is thrown, stack unwinding begins. It destroys bar, and bar better be noexcept, because if bar throws an exception while other exception is in flight, it will terminate your program. So I think I forgot, since C++ 17, destructors are noexcept by default. So this also says that if the base class or an aggregate has a noexcept destructor, the destructor of this class or the aggregate is allowed to be noexcept as well. But if you define explicitly that your destructor is noexcept false, that is, it is allowed to throw exception from within it, it spreads like a wildfire, and your inherited class also has noexcept false destructor, and also aggregate type that has our type bar as an aggregate also has noexcept false destructor. That is, all of these destructors are now allowed to throw exceptions, and this is not desirable because of the multiple exceptions in flight situation. And the core guidelines say that indeed you want to make your destructors noexcept for that reason. And so I know only one exception to this rule. Unfortunately, we have no time for this in this talk. And you'll have to find on your own Andrei's talk, which is called Declarative Control Flow. Let's move on. And now I claim that destructors of the polymorphic types should be virtual. And this one is kind of obscure. So if it goes over your head, it's fine. Just remember that for polymorphic types, the destructor should be virtual. And so here we have a type, a base type for some kind of connection. We have default constructor, we have virtual destructor for some reason, and we have non-virtual methods that allow you to enable or disable the connection and check if it is enabled. So it is used like this. We have some derived classes for no arguments, for one argument, and so on. And instances of that types are used like this. We have a subscribe function that subscribe a connection to the function or functor that is provided for us using make shared, constructs a shared pointer to connection and returns it. And it is used like this. You create a subscription object, you subscribe some function to the subscription, you get a connection, you can notify the subscription, and then all the subscribed functions will be called. And you have connection object that you can destroy to break subscription, and you can temporarily disable the connection. And so the question is, having this contraption where connection base has no virtual methods except the virtual destructor, and having a type that is derived from the base class and having it constructed using make shared, does the base class, the connection base, have to have a virtual destructor? This is kind of the real code from our code base, slightly anonymized, but the gist is there. So we have one group of answers This is, again, this is controversial, but the minority agrees with me that this type shouldn't have virtual constructor, virtual destructor. This is because the type has no virtual methods, and you can't override these methods in the descending inherited classes. And so there is no reasonable scenario where this type can be used in polymorphic sense. That is to construct derived classes and hand it out by pointer to the base type. And also we had the types allocated using shared pointers, and shared pointers do not require types to have virtual destructor because shared pointers remember the actual type that was constructed, and even if you hand it out by a shared pointer to void, the destruction will be performed correctly, and the type doesn't need to be to have a virtual destructor whatsoever. So I would say that in this case, in this particular case, the destructor shouldn't be virtual because the type itself is not virtual. It does not. It can be used in a scenario with virtual with polymorphic like hierarchy. So I again state that the destructor of this non-polymorphic type should not be virtual. And so we came up with this very simple rule. Polymorphic types, for example, types with virtual functions should have virtual destructors. For example, we have here an interface. We define destructor virtual and defaulted, and we have an abstract method and some other virtual method that has default implementation. And we can derive from the interface. We can override the abstract method, and some other types can also derive from the interface and override whatever methods they see fit. And otherwise, if the type is not polymorphic, the destructor should be non-virtual or should not be virtual. And we have the last topic. We surprisingly on time. In C++ 20, we now have so-called constrained destructors. So for this example type, optional, where we have default constructor, we have this constructor that constructs the value, that puts a value into our optional, and we have a destructor that checks if we have a value, and if we have, it destroys it. This is non-optimal because the destructor is always non-trivial, and for trivial types, we would like to have trivial destructors. And so in C++ 20, we now can have so-called prospective destructors, where one of the destructors, or like all but the one destructors, should be constrained. That is, they have to have requires clause. And in this case, we require that our first prospective destructor is viable for types that are not trivially destructible. So we have to destruct them manually. Otherwise, if this requirements doesn't hold, the other destructor, the trivial destructor, will take place. And so curiously, we now can have multiple destructors since C++ 20. So that's the end of my talk. Thank you very much for listening, for participating in my ridiculous quiz. And I ask you to answer the last question. That is, did you learn anything from this talk? And thank you. And here's the the final credit card. Thank you to Howard Hinn and Stephen T. Lavalley and Jennifer Rial for answering my dumb questions and for feedback. And we have 2 minutes for possible questions. In case of copy elision, that is auto A equals build A, which one is guaranteed to be called? So in this, assuming that build A returns some value, let's say that the value that is returned is guaranteed to be constructed in place of A. So in this case, the copy is deleted. Inside build A, you may also write code in such a way that the copy is deleted, and so the copies are deleted all the way from returning from the build A function all the way to the identifier A. So the kind of should be like 2 copies, and both copies are deleted. So you within build A, you construct the object right in the place of the variable A. I hope this makes sense.